What's up, guys? Welcome back to my IB Computer Science video series. Today, we'll be going over topic B2, which covers most of the basic programming skills you need for the course. This video is a Java version. If you're taking the course using Python, please check out the Python version of this video in the description. This video will be structured slightly differently from the syllabus order, as I think IB's organization of the topic is quite ineffective. Instead, I'll be using my own order to teach the topic, while still covering the entire syllabus breadth. Here's the order in which I'll be teaching. This video is meant to be accessible to anyone at any coding level, so you can skip through the video if you're already familiar with some of the topics. I'll leave timestamps in the description and the pinned comment down below. But if you're a complete beginner to coding, I suggest that you watch through the full video starting with the complete basics from chapter 1. So what is coding? You can think of coding as writing ordered lists of instructions for a computer, like giving instructions to a chef. These ordered lists are called algorithms, just like how you would call this set of instructions a recipe. And like chefs, computers execute code line by line starting from line 1, so it's important that we mind the order in which we write code. We're going to be using Eclipse IDE throughout this video to write our code. For our very first line of code, let's tell the computer to print something out. To do that, we write system.out.println, and then specify what we want it to print in these brackets here. So what we do here is we just write quotation marks, and then we type hello world, for example. And to finish this line, we add a semicolon right here. You can think of these semicolons as like full stops. And if you don't add these, then the program just won't run. So make sure you remember them. And now let's run this program. And here you can see in the console, it prints out hello world. We can also define a sentence inside of a variable. So what we can do here is let's make some new lines like this. And let's write string sentence is equal to hello world. And remember our semicolon. We call this declaring a variable, where we create a new variable, sentence, and assign a value to it. So the value is hello world. When we want to access the data inside a variable, we can call the variable by using its identifier, or name. So the identifier here is sentence. So what we can do is we can replace what we wrote inside of these brackets with sentence instead. And when we run the code, it'll have the same effect as what we had before. What we can also do is change the value of the variable anytime we like by using its identifier, sentence, equals, and then let's just write hello earth, for example. And now when we run the program, it will print out hello earth. And that's because we declare the variable here with hello world, but then what we did is we changed the variable to hello earth. And now when we print the variable, we get hello earth instead. When we define the variable, you might have noticed the string keyword. This statement, hello world, and this statement, hello earth, are what we call strings. Strings are one of the fundamental data types in Java. A string is just any combination of characters put together. Other data types include integers, which are whole numbers, chars or characters, which are just single characters, booleans, which is true or false, or double, which is just a decimal number. Variables in Java can only hold one data type at a time, so something like this won't work. And you can see if we try to run this program, we get an error, and that's because we try to store a string inside of an integer variable. Some data types let you perform operations on them. For example, if you have an int stored in a variable, so here we have 5 stored in the variable number, you can then add, subtract, multiply, or divide the value stored inside with another value. So here, we're adding 5, subtracting 5, multiplying 5, and dividing by 5. You can also use the % symbol to find the remainder after division. So now, this variable will take the value 10, this variable will take the value 0, this will take the variable 25, this will take the value 1, and this will take the variable 0 because 5 divided by 5, and the remainder is 0. You can also update a variable using operations. So here we have number was equal to 5. Now this line of code tells the program to add 2 and then update number accordingly. So after this, number will become 7. And there's a special notation for incrementing by 1. It's just going to be putting the identifier and then putting plus plus. And after this, number will become 8. If you have a string, you can concatenate them, meaning stick them together, by adding them together like this. You can also find a string's length by using the length function, or convert all characters to upper or lowercase with these two functions. You can also find the character at a specific location in the string. You just need to remember that the first character of a string has index 0, and it increments by 1 for each subsequent character. Finally, the substring function takes a snippet of the string within a given range. When we specify 1 and 4, we're saying take this snippet of the string ranging from location 1 to 4, but don't actually put in the character in location 4. So now let's just run the program to verify all of this. So we see here that we have concatenated grape and juice into grape juice. And we know that this word's length is 5, so we've got that. We've got everything uppercased over here, and we've got everything lowercased over here. And of course, the index or the character at the index 0 is going to be G, as it's the first character. And the substring should take the second, third, and fourth letter, which we've got right here. You can also compare different values by using any of these comparison operators. The resulting output is a Boolean value, stating whether the comparison is true or false. So because number 1, 10, is bigger than number 2, this result 1 will store the value true because number 1 is bigger than number 2. And if we print result 1, the program will just print true. For characters, the comparison is based off the ASCII code that is assigned to. So here, because C is not equal to G, this result 2 will print out false. And we can see that in action if we run the code right now. You see, we got true and we got false over here. The main use case for these are if statements. An if statement only executes the inside code if the condition is true. So for example, if number 1 is greater than number 2, then run this print statement. And because 10 is greater than 5, if we run this program, we can see that it's printed this line of code right here. But if we change the condition to be less than, now because 10 isn't less than 5, if we run this, then we don't get anything printed. And that's because this code is just skipped entirely. You can also use an else statement like this. Now what this does is, this only runs if the preceding if statement is false. So let's write system.out.println, and let's just write like no, for example. And now if we run the code, we can see that no is printed because this if statement was false. What you can also do is you can say else if. So if this is false, then it checks the second condition over here. So let's say if number 1 is equal to number 2, then print equal. And let's set this equal to 5. Then if we run the code, now because 5 isn't less than 5, it goes to this else if. Because 5 is equal to 5, it will print out equal. If you want to check multiple conditions at the same time, you can use one of these symbols over here. If two conditions are placed like this, with the AND symbol in between, then both conditions must be true for the variable combined to be true. So here, 10 is bigger than 5, so this will be true, but 30 isn't less than 20, so this will be false. And because we have a true and a false, combined will be false. So if we now run this program, it'll print out false. If an OR symbol is used, then only one of these conditions must be true for combined to be true. So because 10 is greater than 5, combined will now be true. And because this is true, it'll run this print statement over here. If you use a not symbol, so like that, then the condition inside of here that we're notting, I guess, is inversed. So because this is true, and we put the not symbol over here, that means that this will become false. What if we wanted to repeat a block of code a set number of times? Instead of pasting the same block of code repeatedly like this, you can use loops. There's two kinds of loops. First is a counted loop or for loop. A for loop repeats code while counting to a certain number. This for loop over here starts at 0, increments by 1 each time the loop is repeated, and when it hits 5, it stops repeating, as this condition becomes false once it hits 5, because 5 isn't less than 5. The number it counts is stored in this variable I, which you can access anywhere within the loop. This for loop simply repeats this print statement 5 times. This for loop prints numbers sequentially from 1 to 5 inclusive, by using the counter variable I in here. Here, I starts at 1 and increments until this condition becomes false. The first instance of that is 6, because 6 isn't smaller than or equal to 5. If we now run this program, we can first see all of these I'm cool messages over here, but we can also see the numbers 1 to 5 printed in order. Here, you can change the number that the loop repeats up to. So here, let's just change this to 10. Or we can change the starting number. So like we can start at 3, or we can change the increment. So let's make this increment by 2 each time. So now when we run this program, we can see it starts at 3, then when the loop repeats once, I increments by 2, so it becomes 5, and then becomes 7, becomes 9. But then when it hits 11, 11 is greater than 10, so this condition is false, so it stops repeating. You can even set the increment to go downwards like this, and if we edit the starting variable and the condition to be something like this, then it'll count down like this. The other kind of loop is a conditional loop, or while loop. A conditional loop repeats the code while the condition inside these brackets holds true. This while loop simply mimics a for loop, where a variable I is set, and each time the loop is repeated, the variable I is incremented by 1, and the loop repeats until I is not less than 5. So if we run it, then we just get 5 instances of this print statement. But remember, this condition can be anything, like for example, while a Boolean variable stays false. You need to be careful with conditional loops to make sure that indefinite loops don't happen. For example, if we take this incrementer out, then run this program, then we just get an infinite chain of I'm cools, which we don't want. You can also write a loop inside of a loop. This is called nested loops. In the case of for loops, make sure to set the loop variable as something other than I. The most common alternative, which we've used here, is j. This code visualizes how the variables I and j change as the program progresses. So at first, we can see that both I and j is equal to 0. And in the next iteration, we see that j has incremented by 1, and it keeps incrementing until it becomes 4. Now, after it hits 4, this for loop has completed one cycle. And after it completes one cycle, it starts again at 0, but this time with I being 1 more than before. So it starts again at 1, 0, and j goes from 0 to 4 again, so it goes up to here. Then again it terminates the cycle, and it starts again with I being 2, and so on. Let's take a closer look at the loop variable I. You'll notice that if you try using I anywhere else in the code outside of the loop, it won't work. This is because of a concept called scope. The loop's variable scope is only within the loop, meaning that code outside of the loop can't see or access it, meaning that this print statement over here won't work. We call the scope local. In Java, other variables that are declared inside of any loops or if statements are also local to that specific statement, like this temp variable over here. But variables that are declared outside of any loops or if statements are called global variables, meaning they can be accessed from anywhere. So this character, C, can be printed. To recap so far, we've learned the fundamental topics in coding: print, variables, if statements, loops, and scope. Let's now move on to a more complicated topic: data structures. Data structures provide different ways to store data other than variables. We'll start with arrays. Previously, you could store one thing at a time per variable. Now, you can store a collection of different items into the same array. To declare an array, we use the same syntax as we did for variables to set the array name, but we use these square brackets in front of the data type to indicate that we're declaring an array instead. Now, we can directly assign values to the array like this using curly brackets, or alternatively, we can define an empty array of size n like this. This array that we call integers is a collection of 5 numbers. Note that trying to put any other data type into this integer array, like a string or a double, will cause an error. Now let's say you want to change the values in this array. You can access individual elements by writing the array name, followed by the index you want to access in square brackets. The first item always has an index of 0, so this will point to the first element in the array integers. And here will point to the second integer of the array. Then you can use the same syntax you would use to change a variable's value. So this code would change the first element in the array to 13, and this code would change the second element to 6. Now let's look at how to traverse through an array. One way is to use the dot length operation. With this, you can use indexes to individually access each element. So here we have an array of numbers with 7 numbers stored inside. And this for loop starts at I equals 0 and increments by 1 each time. And this code prints out numbers 0, numbers 1, numbers 2, and so on until 6, as the length of the array is 7. So here, if we run the program, we can see that it starts at 5, 3, 8, 1, 2, 9, 4. There's also a nice trick to simplify this with for loops, called the for each loop. This code over here means repeat the loop for every element present in the array. And every element that it loops through is stored in the variable number. Then you can sequentially access the array's contents by using the variable number. So again, we've got 5, 3, 8, 1, 2, 9, 4 printed as well. You can also nest arrays inside of arrays. This results in higher dimension arrays, or 2D arrays. To define these, you first need two sets of square brackets next to the data type, as opposed to one pair for regular arrays. Then, if defining the values directly, you need to nest the subarrays into a larger array, like this. So we have a subarray here, a subarray here, and a subarray here, which are all contained within these outer curly brackets. If you want to create an empty 2D array, you need to use two square brackets like this, specifying the number of rows and columns. So here, we're declaring a 2D array with 3 rows and 3 columns. You can think of a 2D array like a matrix of data, where the subbed arrays represent different rows, and the data takes up different columns. To access different parts of a 2D array, you can do one of two things. If you want a specific subarray, so a specific row, like this one, you can put the row index like this, and this will return the specified row. And this row is a 1D array technically. So you can store this, so we're storing this inside of the variable row1, and this row1 variable is the type integer array. And so this row1 stores this row, row2 stores this row, and row3 stores this row. If you want a specific element in a specific row, you can put the row index over here, then specify the column index. This will return the specific item in the specified row and column. To iterate through a 2D array, you need to use nested for loops. If you're using indexes, you can use this kind of syntax. It's basically what we looked at earlier, but you use the amount of rows and columns for your stopping conditions. So here we have I is less than 3 and j is less than 3 because this 2D array has 3 rows and 3 columns. Then you put the loop variables I and j like this. If we run the program, initially I is equal to 0 and j is equal to 0. So this prints out the element in row 0, column 0, which will be this number right here. Then j increments by 1, so it'll print out more numbers 0, 1, which will be this number. And then increments again, 0, 2, which will be this number. Then I increments by 1 and j resets to 0, so it'll print out this number, and so on. It's a bit more complicated with for each loops. So for your first loop over here, you need to retrieve each row in the array like this. And then for the second loop, you need to retrieve every element in the retrieved row. So notice how the data type here is int array, because each row is technically just a 1D array. And then we just do int call, so for every element inside of this array row. And so this variable column or call will contain every element in the 2D array over the entire loop, going through each element in a row before moving on to the next row. So again, it'll move in the order 2, 9, 4, 1, 7, 5, and so on. So let's try just run the program. And there we go. We see 2, 9, 4, 1, 7, 5, 3, 7, 3, 8, 6. And then it starts again because, of course, we're doing it twice. 2, 9, 4, blah, 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 blah. So that's the basics of arrays in Java. But one key limiting factor in arrays are their fixed sizes. We can circumvent this problem using something called array lists. Array lists are not part of the fundamental Java language, which means we must import the array list package at the top of a program like this. Array lists are dynamic in size, and we can add as many elements as we want to the array list, although they must all be of the same data type. To define an array list, we can use this line of code right here. The array list R can store as many integers as the user wants. The same index rules from arrays apply here too, where the first element starts at 0 and it increments by 1 every time. To add elements to array lists, we use the .add function. It assigns the next available index to the element in the brackets. So here, 3, 6, 7, 2, 9. To remove elements, we can use .remove. But this time, in the brackets, you must specify a valid index to remove. We can also get the element at a specific index using .get, or get the index of a specific element with .index of. .size gives you the size of the array list, and .set allows you to replace the element at an index with another value. Then, we can use a similar method to regular arrays to print out each value in the array list. So here, we use a for each loop. Let's now look at two special data structures, stacks and queues. You can think of a stack data structure as a literal stack of plates. When you add a new plate, the plate is put at the top of the stack, and as you add more plates, it stacks up. When you want to retrieve a plate, you have to take it from the top of the stack. This is the principle of a stack data structure. It operates using the last in first out principle, or LIFO. There's 4 key operations that you can do on a stack. First is push, which adds a new element onto the stack. We've added 5 numbers to the stack here, which results in the stack looking like this. There's also pop, which retrieves and removes the element at the top of the stack. So since pop 1 stores the first pop, it stores 8, and pop 2 stores 3. And the stack is then left looking like this. There's also peek, which only retrieves the element at the top of the stack without removing it. So the variable peek here stores the value 9, but 9 isn't removed from the stack. It stays. And lastly, is empty, which checks if the stack is empty. Since we still have elements in the stack, this print statement will print false, as you can see right here. Next up is a queue. You could think of a queue data structure as a literal queue of people. People enter the queue at the back of the queue, and people are removed from the queue from the front. This is the first in first out principle, or FIFO. Key operations include enqueue, which adds an element to the back of the queue, dequeue, which retrieves and removes the element at the front of the queue, front, which just retrieves the element at the front, and isEmpty, which checks if the queue is empty. Notice how these operations are all similar in function to stacks, but using FIFO instead of LIFO, and using different words to describe the actions. And that's all you need to know about data structures. So to recap, we've got arrays, 2D arrays, array lists, stacks, and queues. We're now going to move on to modularity. Modularity is when a big program is comprised of separate components that work together to make up the complete program. So instead of a big mosh pit of code squished together, code is usually structured so that different problems are solved by different chunks of code. For example, when making a calculating program, you can break the problem down into these 4 steps. Each of these can then be considered separate problems until it's time to assemble the final program. Modularity makes the code more reusable, easier to understand, and easier to trace an error when there's a problem with the code. Java implements modularity using functions. A function is a block of code defined by the user that can be ran in the code whenever the user wants. To define a function in Java, use this syntax: public static void, and then your function name. This code defines a very basic function. We're calling it simply prints function. Now that we've defined the function, we can call it with a function name along with a set of brackets in the main over here. Now, when we run the program, the contents of the function is ran once, like so. We can call this function multiple times, so we can just write func and then brackets and then semicolon, and then we just do it again, and we just do it however many times we want. And this leads to function being printed out multiple times. Or we can edit the function itself to do more things, like print more lines. So we can just write system.out.println I'm a function. And now we're calling this function 3 times. So let's run this, and boom, we've got function, I'm a function, repeated 3 times. But a function can be more than just a glorified container box for code. We can also define inputs for the function and make the function output a value as well. This is analogous to functions in maths. In maths, you define an input x, and then the function spits out an output f of x. To define inputs, you add parameters into this bracket next to the function name. These are your variables that you will input whenever you call the function. You could then use these inputs inside of the function. So here, I've told it to take a number x, add 5 to it, and then print the result. So now, when I call the function, so we write f, I must define an input x inside of these brackets. So let's say we define x to be 5. And now when I run this program, it takes my defined value 5, adds 5 to it, and then prints out 5 plus 5, which is 10. Function calls can also become values. To achieve this, you need to use the return keyword. The return keyword's job is to give function calls a value and close the function. So instead of printing 5 plus x over here, we're returning 5 plus x instead. Then, when defining the function, you need to define the data type of the return value. Remember when we defined a function using public static void? Void just meant that the function doesn't return a value. But now, by saying int, we're saying the function is returning an integer value. When I call my function down here, the function call becomes an integer, as we've returned an integer value 5 plus x. So this f of 5 actually just means 5 plus 5, which is 10. And we're going to store that into this variable result. So now we can print out this result, and that should just be 10 again. The return keyword can also be used to end function calls early, only when the return type is void. By simply saying return like this, it tells the function to terminate without returning a value. But here, we can't do that because we can't return nothing when we specified the data type to be int. So this has to be void, and we have to remove this line. Let's make an example function, add. We want the function to take two numbers, sum them together, and then return the sum. So firstly, we can define the function add, so public static, and then we want it to return an integer value, so let's write int here, and then add, and we want it to take two parameters, int a and int b. And let's open the curly brackets. And now inside the function, we want to add these two inputs together, so let's define another variable, int c is equal to a plus b, and then we can return c. And there we go, that's it. And now what we can do is we can call the function in here, so we can call add, and let's say 5, 3. And then we can, and because this function returns an integer value, we can store the result inside of here, like this. And then we can just print results, and what we get is we get 8 over here, which is to be expected. There's a special trick that can be used with functions as well, called recursion. Recursion is the act of calling the function inside of the function itself. To understand recursion, we need to get a bit technical. Let's look back at the add function, and imagine this call and the print is within main. When the function is called, it's put into something called a call stack. While the call is executing, it exists in this call stack. If the call terminates, either by going through the entire function or when a return keyword is reached, the call is popped from the call stack, and a value is returned. The return value would be null for void functions. So here, the call is popped with the value 5, and the call itself then takes on the value 5, which is then put into the variable sum. But in recursion, function calls can't finish without reaching the recursive call first, meaning additional calls are repeatedly put into the call stack while the original call gets stuck. So here, when the function is first called, it goes to this if statement, but then it hits another call, recur 4 minus 1, or just recur 3. This new call is then pushed into the call stack, and again, the call is ran until another call is hit, so recur 3 minus 1, or recur 2. The only way to exit this loop is for a function to not call itself, which it doesn't in the case that this recursive function is called with a value of 0, as it doesn't fulfill the condition in the if statement. In this case, the print line and the call itself is skipped, so recur 0 finishes, which then allows recur 1 to finish, and the calls in the stack are then popped in order. The total output of this recursive function would be 4, 3, 2, and 1, as this print statement for 4 came first, then for 3, then for 2, then for 1, and since 0 isn't greater than 0, this print line would never execute, giving us this output over here. The important thing to note is that when a call is stuck because of recursion, the call cannot proceed. In this modified recursive function, where the self call is put before the print statement, the print cannot run until the self call is sorted. So again, this call stack fills up, and after the call recur 0 can't call itself, the call stack starts to unwind. But in the call recur 1, only now is the call recur 1 minus 1 sorted, meaning the print statement can only now execute. The same happens for recur 2, recur 3, and recur 4, meaning that the resulting output is therefore 1, 2, 3, and then 4. Let's look at another example of recursion. This recursive function calculates the factorial of an input number. Let's say this function is called with a value of x equals 4. So the call factorial 4 enters the call stack. Since 4 is bigger than 1, it goes into this else branch over here. It says to return x multiplied by the function called with x minus 1. This means that the function call factorial 4 will return or equal the result of 4 multiplied by the function call factorial 3, which also enters the call stack. Now let's focus our attention onto this new call. Since 3 is still bigger than 1, it goes into this else branch again, so factorial 3 then returns 3 multiplied by factorial 2, because 3 minus 1 is 2. And now this new call enters the call stack, and now 2 is still bigger than 1, so it still returns this value over here, So we can say equals to 2 multiplied by factorial 1. And factorial 1 also enters the call stack. But now 1 is equal to 1. So it fulfills this condition right here. So this call will return 1. And because we've returned a value, this call then terminates. And now factorial 1 then takes the value 1. That means that factorial 2 can now terminate because it's returning a numerical value. So this returns 2 times 1, or just 2. So that's popped, and now factorial 2 takes on the value 2. And again, factorial 3 then takes on the value 3 times 2, which is 6. So that's also popped, and now this factorial 3 takes on the value 6. And now finally, our original call, factorial 4, takes on the value 4 times 6, which is 24. So when we run this program, it should theoretically print 24. There we go. Now for recursion to work, two things must be included in the recursive function. First is the presence of a base case. In the factorial example, the base case was that if the parameter is 1, return 1 for the function. Secondly, you must ensure that when you recursively call the function, the new parameter gets closer to the base case each iteration. In the factorial function, every time the function was called, the number got closer and closer to 1. So factorial 4 went to factorial 3, went to factorial 2, and factorial 1, which then got to the base case. These two conditions ensure that the recursion doesn't go on indefinitely. Let's go over another example of when recursion is used in programming. Hopefully, as we go through examples, you'll start to get the gist of when recursion can be used. In this function, we find the value of the nth term in the Fibonacci sequence. The fundamental definition of the Fibonacci sequence is that the first and second terms are 1, which we put as the base case over here. So if the input n is ever 1 or 2, meaning the first or second terms, then simply return 1. Then the third term would be the first term plus the second term, the fourth term is the second term plus the third term, and so on. Let's trace what happens when the function is called with n equals 6. So the call Fibonacci 6, let's just shorten as fib6, is equal to fib4 plus fib5. Now fib4 we can just put in the call stack, fib4 is equal to fib2 plus fib3. And we know that fib2 is just going to equal 1, so we can just put 1 over here. Now fib3 is equal to fib1 plus fib2, and both fib1 and fib2 are equal to 1, so we can just put 1 and 1 here. And because we have 1 plus 1, fib3 will just return 2. So fib3 will be popped, and fib3 takes the value 2. And then fib4 will take the value 1 plus 2, which is 3. So this will also be popped, and fib4 takes the value 3. And now we can focus on fib5. Fib5 is just equal to fib3 plus fib4. And from before, we know that fib3 is just equal to 2, and fib4 is just equal to 3. So fib5 takes the value 5. So we can just remove that, and fib5 will equal to 5. And then our original call, fib6, will just equal 3 plus 5, which is 8. So theoretically, this program should print 8. There we go. When writing recursive algorithms, try doing these two things before writing any code. First, try identifying the base case. This is a fundamental definition for your problem. For example, in factorials, the fundamental definition is that 1 factorial equals 1, and in Fibonacci, it's that the first and second terms are 1. Then, try writing the problem in terms of simpler versions of the problem itself. For example, 4 factorial can be written as 4 times 3 factorial, and 3 factorial can be written as 3 times 2 factorial, and so on. Each iteration is simplified by using the definition of the factorial until we reach 1 factorial, whose fundamental definition is 1. In the Fibonacci sequence, the nth term can be written as a sum of the n minus 1th term and the n minus 2th term, and each of the terms can be written again with that definition until you get to the fundamental definitions that the first and the second terms are 1. Recursion is great for solving certain problems with minimal code usage, but most times, recursion makes solving problems unnecessarily difficult and complex. It also uses up a lot of memory due to the call stack. If the exam questions don't specifically ask you to use recursion, don't be pressured to use it. And that's it for modularity and functions. Everything you've learned so far are used very frequently in coding. However, the next 2 chapters will cover slightly more abstract topics. Before we get into the new syntax in the chapter, let's talk about errors. In coding, there's 2 kinds of errors. Runtime errors are errors that happen while the code is running. This is different from compile time errors, which are errors in the actual code, like incorrectly writing syntax or using uninitialized variables, preventing the code from running at all. Examples of runtime errors include resource shortages like memory, invalid operations, invalid input, or trying to access array indexes that doesn't exist. Compile time errors are shown with red lines in most IDEs, so they can usually be solved before executing the code. Runtime errors are a problem because it causes the entire program to stop working, and they are usually random and unexpected. Fortunately, there is a way to deal with runtime errors, the try-catch block. The try-catch block is a way to predict a certain runtime error, and provides a way for the program to continue if it encounters said runtime error. For example, this program has a divide function that divides two integers and returns the result as an integer. This function works for any combination of two integers, except for one scenario, when the second input is 0. If we try this, let's run the code, we get a runtime error, arithmetic exception, divide by 0. Let's note that down. Now, since we know that there's a possibility that this exception could occur, we're going to predict it using a try-catch block. So how you write a try-catch block is you write try, curly brackets, and then you write some code in here, and then here we write catch, and then brackets, and then another set of curly brackets. So how this works is that we're going to try running a piece of code. So we're going to try running this code. Now in the catch block, in these brackets here, we're going to write the exception that we're predicting in these brackets. So we're going to predict the arithmetic exception. And we just write E over here as well. And now, if this error happens while the code inside the try block runs, the program will run the code inside this catch block instead of crashing like it did at the beginning. So in here, let's just say system.out.println cannot divide by 0. And now if we run the code, instead of crashing and giving us an arithmetic exception, we get this print statement, cannot divide by 0. The program doesn't crash anymore. I should add though that exception handlers aren't necessary in most cases, especially in an IB exam context. So when you're writing code for an exam, unless they specifically ask you to use exception handlers, you don't have to think about these try-catch blocks much. Like in this example, an if statement would be a much more intuitive solution. So up here we can write if b is equal to 0, then just return -1, for example. But there is one specific situation where you absolutely must use exception handlers, file processing. In this chapter, we'll learn how to write to and read from files, and understand why exception handlers are very important here. Let's start with FileWriter and writing a text file. FileWriter is a library that can access and edit text files. So we start by importing the FileWriter library, which we've done over here. Now, we can open a new text file by writing this line of code. FileWriter fw is equal to new FileWriter. And then in these brackets, we specify the name of the file that we want to write to. So let's try output.txt. So this line opens a new file, output.txt, for us to write in. Now, if we want to write something, we write fw.write. And then in here, we write whatever you want to write. So we can write something like hello, for example. And then if we want to write anything else, we write fw.write. And then we can write something like I'm Jerry. But if we were to just leave it like this, the program would just write hello, I'm Jerry, all in the same line. If we want to separate them, we can use /n over here. What this does is it tells the program to enter a new line after it's written hello. And then finally, we need to close the file writer after we're done. So we write fw.close. And this is mandatory because if you don't have this, then the program doesn't write properly. So theoretically, this code should make a new text file called output.txt and write 2 lines and then close. But look what happens. When we try to run the code, there's an error. There's an unresolved compilation problem. The reason is because Java wants us to handle something called an I/O exception. An I/O exception is a runtime error that can randomly happen because of memory issues or hardware failure. To handle this, we need to use another try-catch block. So let's just write another try-catch block, just an empty one for now. So what we need to do is we need to take our code and put it into this try block. And what we're predicting that to happen is an I/O exception. So we just write an I/O exception over here. And now, if this exception is caught, we can write like something like system.out.println, like error, for example. But a better solution is to write e.printStackTrace, because What this does is if an error occurs, it tells us what went wrong inside of the console. So now if we try to run this, there's no error. And there should be an output.txt stored somewhere. So this is the Eclipse workspace that I'm working in, and this is a project that I'm working in. So let's see. And boom, there is an output over here. And if we open it, we get exactly what we wrote. With FileWriter, we can also append new text to an existing file. If we were to run this program again with another file, the program would replace the old output text file with a new output.txt, this time with an extra line. So if we write fw.write, this is another line, and we were to run this program, instead of hello, I'm Jerry, and then hello, I'm Jerry, this is another line, we would just get these 3 lines in one text file because it overrides the old one. But we can change this so that the file writer is in append mode, and the way we do that is we just stick a true in front of here like this. And now if we run the program, we can see that it appends hello, I'm Jerry, this is another line onto what we've already had before. Now let's learn how to read files using Scanner. Scanner is a library that can open and read files on its own. This is an algorithm that reads and prints an entire text file into the console. Let's analyze how it works line by line. We start by bringing the file into the code. To achieve this, we use the file library, and we store the file output.txt into the variable file. Now, we use this line of code, which similarly to FileWriter, tells Scanner to open the file. We can track where Scanner is reading the file using the variable scan. Initially, Scanner starts from the top line of the file. If we wanted to read a line, we use scan.nextLine. This returns the line in the file it was on and moves on to the next line. So after running this once, we've read the first line, and now Scanner is ready to read the second line. We can use a while loop to repeat the next line method. We want it to keep reading until there are no lines left to read. We can do that by using hasNextLine, which is a method that returns true if there is a next line. So if there is no text to read, this will return false, meaning the while loop will stop. So overall, this while loop is saying that while there exists text in the file, read off it and print it. That's how we print the entire file out. So let's try to run the code here. And there we go. This is the output.txt that we've written with our FileWriter program. Lastly, we can see scan.close over here that closes the scanner just like how we close the FileWriter. And with the try catch, the exception we're catching here is file not found, where the file output.txt might not exist in the project directory. But since we made an output.txt from the FileWriter example, it reads the text file that we wrote earlier for us. We've now covered all the basics of Java that you need to know. Now it's time to bring all the concepts together for the final topic, algorithms. This is where we'll be looking at code made to solve actual problems, instead of just code for the sake of it. Firstly, let's understand how to analyze a given algorithm. We do this using trace tables. Trace tables are just a way to track how an algorithm runs by looking at how the internal variables change over time. Take this algorithm that takes in an array and increments one of 2 variables depending on whether the array element is odd or even. Let's make a trace table for this algorithm for this input array. In this algorithm, there's 3 variables, I, odd, and even. I takes the value of every element in the array, and odd and even change depending on the value of the input array. So now let's fill in the table. So let's just divide them into columns over here. So initially, I doesn't have a value, and odd and even are at 0. So let's just write 0 for both of here. Now firstly, I takes the value 5, because this is the first element in the array. So we can just write 5 over here. And since 5 is odd, because 5 modulus 2 is not 0, odd increments by 1. So we can write 1 over here, and even stays at 0. Now for the next element, 2 modulus 2 is 0, so we know that it's even. So let's write 2 over here, and odd stays at 1, because odd doesn't increment, and even increments by 1 as well. And we can keep doing this for every element. So you have like 9, 3, 12, 4, 1, 11. So 9 is odd, so this increments. 3 is odd, so this increments. 12 is even, so even increments. 4 is even, so it increments here. 1 is odd, and 11 is odd. And there we go. This is our trace table for this algorithm over here. By using truth tables, we can pinpoint where errors happen, analyze how variables change over time, and understand how an algorithm works. It's important that algorithms solve problems in the most efficient way possible. This means that algorithms use as little time and memory as possible. But how do we measure this? We can't measure exactly how many seconds an algorithm runs for, or exactly how many bytes of memory are used. Instead, we use something called time and space complexity. These tell us how much time or space is needed relative to the size of our input data. Let's look back at the algorithm we looked at. We need to consider how much memory and time this algorithm is using. Let's start with time. If the input array is size 8, like in this example, this for loop over here would loop 8 times. If the array was size 5, the loop would loop 5 times. And if the array was size n, so any size, the loop would loop exactly n times. In this case, we say that the time taken as a function of n, or t of n, is just equal to n, meaning input size and time taken has a linear relationship. Thus, we say that the algorithm has a time complexity of O n. But no matter how big the input array is, the algorithm only ever defines 3 variables, I, odd, and even. These variables then takes fixed portions of memory. Since these portions of memory are the only memory used, we say that the space complexity of the algorithm is constant, or just denoted as O of 1. When finding time and space complexity, it's useful to draw the truth tables for the algorithms so you can visualize how many iterations it takes for different input sizes. These are some of the possible values for the big O notation. Each big O notation represents a different relationship between the input size n and the time taken Tn, or the memory used Sn. But one important note is that Tn and Sn aren't actually time and space complexities. It's the big O notation that you need to write. So even if you find the relationship in an algorithm between time and input size to be T of n is equal to 2n, for example, you still need to write your final time complexity as big O of n, because the coefficients don't actually matter for time complexities and space complexities. It's all about the overarching relationships. Now let's go over all of the algorithms you will need for this course. These can be categorized into search algorithms and sort algorithms. We'll cover search algorithms first. The linear search is one way to search a data structure like an array. This algorithm searches through an input array for a value. To do this, the code starts at index 0 in the array and compares the item in the array to the search value. If there is no match, the code moves on to the next index and repeats this until the item is found, in which case it returns the index that it found the item in, or until the entire array is exhausted without finding the item, in which case it returns -1. And if we try to run this program over here, we get the value 6, and we can verify this by just looking at the array. So this is index 0, 1, 2, 3, 4, 5, 6, and this is the value that we searched, so we know that this linear search is working properly. Key advantages of linear search include that it's simple to implement and it works on an unsorted array. Its time complexity is O(n), and its space complexity is O(1), as the possible amount of iterations depends on the size of the array, and it only ever defines one variable, I. The other searching algorithm is binary search. Binary search only works on sorted arrays. How it works is it finds the middle value, compares the target value to the middle value, and then rules out the half that must not contain the target. This process repeats for smaller subarrays until the target value is narrowed down. For example, in this example input, say we want to find the value 66. We first retrieve the middle value, which is 31. Since 66 is bigger than 31, we can now rule out 31 and this entire left side of the array. So we can just put a little crossover. And now let's focus on the smaller array over here. In this smaller array, the middle value is now 60. Since 66 is still bigger than 60, we can now rule out 60 and this left side of the array as well. And now we're down to this small array over here. In this smaller array, 66 is smaller than 74, so we rule out 74 and then we eliminate the right side of the array, so all of this. And now the middle value here is just only one value, it's 66. Thus, we found our target value in only 3 iterations, as opposed to if we used linear search, it would have taken us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 iterations. Here is a function that performs binary search on an input array R, searching for an input. We first define variables low and high to point to the array's first and last element. Then, we define middle as the middle element by taking the mean of the low and high pointers. We then compare our target value to the array's middle value, and we update the low and high pointers accordingly, which essentially narrows down the array. Here's a visual diagram for what's going on. You can see that the low, mid, and high variables point to their array elements. The code low equals mid plus 1 that we just saw essentially puts our low pointer right here, which essentially eliminates this half of the array. as the pointers low and high are now limiting the array to this little subsection over here. And inversely, the code high equals mid minus 1 puts the high pointer right here, limiting the array to this little section right here. And then after that, we calculate the mid again. So we put the mid over here. And then again, if the variable that we're looking for is greater than, then we put low over here. And if it's less than, then we put high over here. And this continues until the mid variable is the value we're searching. So if the middle value is ever our target, we return the middle index as the index we searched for over here. We want this to loop while the array still has unexplored areas, meaning when our low variable is less than or equal to our high variable, because our low variable being in a higher array position than our high variable wouldn't make sense. If this condition isn't true, that means the entire array has been exhausted without finding our target, meaning that the search was unsuccessful. So we return a -1. This algorithm has a time complexity of O log n and a space complexity of O of 1. If we try to run this program, we get 7, and we can verify this by counting in the array. So we have 0, 1, 2, 3, 4, 5, 6, 7. And that is the exact index that we searched for in this call. Now let's move on to sorting algorithms. We need to be able to sort an unsorted array. In coding, there's a lot of different ways to do this, but for this course, we'll be looking at bubble sort, selection sort, and for HL, quick sort. The first sorting algorithm is bubble sort. Bubble sort works by repeatedly swapping adjacent elements until the array is sorted. Let's say that we want to sort this unsorted array in ascending order. So we start from the left, and we start with these two adjacent elements. So we ask ourselves, is this element greater than this element? In this case, since 13 is bigger than 8, we swap these two elements around like this. And now we look at these two adjacent elements. So is 13 greater than 35? No, so we don't swap anything. And now we look at these two. Is 35 greater than 26? Yes, so we just swap these two around like this. And then finally we look at these two. So is 35 greater than 19? Yes, so we swap these around. So now we've gone through the entire array once, and we call that a pass. But notice how the array still isn't sorted yet. So we need to repeat this pass again, starting from the left again. So again, is 8 greater than 13? No, so we leave this. Is 13 greater than 26? No, so we leave this. Is 26 greater than 19? Yes, so we swap these around. And we don't have to do this one anymore because we already know that this will be greater than anything beforehand. So now we've completed another pass, so let's try again. So is 8 greater than 13? Nope. Is 13 greater than 19? Nope. Is 19 greater than 26? Nope. And is 26 greater than 35? Nope. So if we've answered no to every single comparison in a pass, that means that the array is completely sorted. And that's evident here because it is sorted. 8, 13, 19, 26, and 35. This is the algorithm for a bubble sort in Java. The function takes in a single array, R, as an argument, and will return the sorted array. If this algorithm looks tedious right now, don't worry. This algorithm does exactly what we described just now. So try matching up what I say here with a visualization of the bubble sort we went through just now. We first define n as length of the array. Now, we define the number of passes through the array as n minus 1 inside of this for loop. We then define a Boolean variable, swap. This will determine if during a pass through the array we have swapped at all, and you'll see why this is useful in a bit. Now, let's actually loop through the array and swap some elements. We want to loop through the array minus the elements we've swapped already. So we'll go through this loop until n minus 1 minus I. The I here will ensure that we don't loop through the already sorted elements. Now, since j starts from 0, we can access the first two elements in the array with rj and rj plus 1. We now compare these values, and if rj is bigger, we swap the two elements with this code over here, and then set the swap variable to true. This repeats for every adjacent element from left to right until the loop terminates. So elements 1 and 2, elements 2 and 3, elements 3 and 4, and so on. Once the loop has reached the end, that's one pass complete. If there were no swaps in that pass, then this swap variable would still be false. So if that's the case, we tell the loop to stop entirely, finishing the algorithm. This is because in this case, we know that the sorting has finished, as there were no swaps in that pass. Finally, after everything's done, we return the sorted array here. Now when we sort this example array over here and run the program, we can see it is now sorted. The time complexity of bubble sort is O(n)², meaning that in the worst case, for an input array of size n, a total of n squared iterations need to be performed. And the reason for that is because of this nested for loop. And the space complexity stays at O1, as the defined variables are constant for any array of size n. A second method of sorting is selection sort. Selection sort isn't just mindless swapping between elements like bubble sort. Instead, it chooses beforehand the maximum or minimum value, then makes a swap. Let's understand this using a descending order example this time. In this example array, we see that 35 is the maximum value, and since the maximum number needs to be at the very left in descending order, we need to put 35 at this leftmost spot. But 35 isn't at the front of the array as it should be right now. So now, we swap it with the element at the leftmost side. So we swap these two around, like this. And that's one pass through the array. Now, we find the next maximum, 26. This is also not at the front, so we swap it with this next element over here. So we just do that. And now we keep going. So in this little subarray, 19 is the maximum, but this is also not at the leftmost side. So we just swap this like this. And then lastly, 13 isn't where it should be, so these are swapped. And there we go. That's descending order right there. This is the algorithm for selection sort, also taking in a single array R. This time, we wrote our algorithm to sort in descending order. We define n to be the length of the array again. Then, we define the number of passes through the array as n minus 1 in this for loop, just like we did for bubble sort. Now for each pass, we define two variables, max num and max index. Then we loop through the array again from I to n. The reason we do I to n is because after each pass, we want to ignore the element in the array that's already been sorted. With this code over here, we find the maximum value for the unsorted elements and store its index into max index. Now that we found the maximum value, we just need to swap the leftmost element with the maximum value with this code over here. That completes one pass. We've now put the largest value to the far left. This repeats until the full array is sorted, and we finish by returning this sorted array. Now if we input this example array into the function and print it, we get a successful descending order array. Now if we wanted to do ascending order, we would need to change the code so that it finds the minimum value each pass and swaps it with the leftmost element. The time complexity of selection sort is also O of n squared. And again, that's because of this nested for loop over here. And the space complexity stays at O of 1. So when would you use bubble sort versus selection sort? Well, to be honest, both are actually really inefficient in the world of sorting algorithms. Their time complexities of O of n squared make them terrible at sorting large datasets. But they do have some specific advantages over each other. Bubble sort is good at sorting almost sorted datasets. It can know preemptively when an array is sorted thanks to the swap Boolean variable. Selection sort is good because of the reduced amount of swaps in a very unsorted dataset. Remember, to execute a swap, we have to execute these 3 lines every single time. And also, these use space due to the temporary variable temp. So in cases where writing to new variables is computationally expensive, selection sort can beat bubble sort in efficiency. Let's now explore another sorting algorithm, quicksort. This method uses a divide and conquer strategy, much like binary sort. To start, we need to pick a pivot. The pivot can be any number, so we'll just pick this last element over here. Then, put every number less than the pivot to the left of the pivot, and vice versa for every number greater than the pivot. So let's just put 54 in the middle over here. And now we need to put every single number less than 54 to the left. So 35 goes here, 7 goes here, 16 goes here, 11 goes here, 43 goes here, and 22 goes here. Let's just make some space here. There we go. And now we need to do the same for every element greater than 54. So 61, 98, 79, and 82 all get moved to the right. And now we need to repeat this exact steps for these two subarrays created. So this left side of the pivot and this right side of the pivot. So again, we need to choose another pivot. So let's just pick 22 again, and then do the exact same thing. So 7, 16, 11, and then 35 goes to the right, 43 goes to the right. And then here, again, we pick this pivot, and then we arrange it like this. And 54 just gets put here. And if we keep doing this, if we keep repeating this, eventually the entire array gets sorted. It might sound complicated on paper, but in practice, this beats out both bubble sort and selection sort in time complexity, with average time complexities of O and log n, albeit with a space complexity of O log n. but implementing quicksort is arguably the most complicated. Here's the code for it. As you can see, it has two recursive terms. This is where the extra space is needed, as we need extra memory for the call stack. Let's analyze this code line by line. So here, we have our base case to prevent infinite recursion. It ensures that recursion stops once arrays of sizes 1 and below are reached, which we know can't be sorted anymore. Next, we define our pivot as the input array's last element. Now comes the hard part, moving the elements around the pivot. I'm going to show this in another visual diagram. To do this, we start by defining a pointer that points to the first element, so right here. This pointer will be very important. Then, we loop through every element in the array with a for loop. For each element, if they are less than the pivot, we swap them with the element that the pointer we defined is currently pointing to, and then we increment the pointer. When we do this, we make sure that all the elements that are less than the pivot are pushed to one side, and the rest to another side. So let's see this actually play out. So we start with this element. Is 35 less than the pivot? Yes. So now what we do is we swap it with the element that pointer is currently pointing to, but since they're pointing to the same thing, nothing happens. And now pointer is incremented up here, and now that's one cycle done. So now I is incremented to the next element. So now is 7 less than the pivot? Yes. So the exact same thing happens, but there's nothing to swap here. So again, pointer increments, I also increments. And now is 16 less than the pivot? No, yes. So again, the same thing happens, nothing happens. Pointer increments, and I increments. And now, is 79 less than the pivot? No. So pointer doesn't move, there's no swaps, and I just simply moves on. Now, is 82 less than the pivot? Yeah, nope. So again, pointer doesn't move, and I just moves on to the next one. And now, is 11 less than the pivot? Yes. So now, what we do is we swap these two elements around, like so. Pointer increments. And now I also increments over here. Now again, is 43 less than the pivot? Yes. So again, we swap these two around. Increment pointer. And then I is incremented again. Now is 61 less than the pivot? No. So we just move on. Is 98 greater than the pivot? No. Then we just move on. Is 22 less than the pivot? Yes. So now we swap these two around again. We increment the pointer, and now since we've reached the pivot, we don't actually count this pivot, so I just stays here. And now the crucial point is that the pointer is now pointing at the first element that is greater than the pivot. You see, every single element that's less than the pivot is now put on this left side, and pointer is pointing to 82, which is the first element that's greater. So now all we have to do is we just have to swap the pivot element with the element that pointer is pointing to. So if we just swap these, like so, boom. Now every single element that's less than the pivot is now on this left side, and everything that's greater is on this right side now. All of this code over here recreates what we just did. So first, we set our pointer as the lowest element in the array. And now we loop through the array until the element right before the pivot, which is why we put high -1 over here. And now what we do is we compare every single element that I is pointing to the pivot. So if they're less than the pivot, we swap them. We swap the elements that I is pointing to with the element that pointer is pointing to. And then we increment pointer. And we keep doing this until I reaches the element right before the pivot. And then once that completes, we just swap the pivot element with the element that pointer is pointing to, which then completes the entire shuffling. And then finally, we have our recursive statements. We write it like this to first sort the left side of the array. So we do the recursive thing for the left side of the array, for the left side of the pivot, and then the right side. Remember, this entire algorithm happens for each subarray, meaning each small subarray gets sorted, which then sorts the bigger subarray that is part of. And then after all the calls are popped from the call stack, we're left with a sorted array, which we return over here. And now if you run this code, boom, we have this entire array sorted in ascending order. And that's all you need to know for basic programming skills. But there's a lot more programming in the course, especially for HL, so be sure to check out my videos on B3 and B4 later. But for now, thank you for watching.